So a very good morning and welcome to the second day of this workshop. In this first lecture, I'm going to talk to you about transforms. And as Professor Patwardhan said yesterday, the purpose of this lecture is not so much to teach you about transforms, although for some of you that might also happen, as it is to actually put forth a pedagogical approach to dealing with transforms. Naturally, if one wants to understand how to teach transforms, some amount of teaching is required. But the difference is that we shall do it in a manner that you might want to replicate in your own institution, which means that I'm not going to teach and you're not going to learn. You're going to be active participants in the learning process. As Dr. Patwardhan said yesterday, and Dr. Mrinal Patwardhan and also Professor Sachin Patwardhan, our whole purpose of these sessions and all this whole workshop is to expose the idea of active learning, and we are going to practice that when we learn about transforms today. Now also, I would like to reiterate that we will operate group-wise. And that's why I have requested all of you to sit as per your groups, and this practice will continue throughout the workshop now. The idea is that you need to get to know your group partners very well, and that can happen best when you sit in proximity and talk to one another regularly, and also interact in the active learning exercises that you do. So therefore, please make it a point to sit as per your seating arrangement now, and continue to interact with your group partners all through the workshop. Right? And in particular in this session. Well, transforms are used by all engineers, and not just engineers, they're used by scientists, they're also used by social scientists. They're used by anybody who wants to deal with data. In fact, while the electrical engineer in some sense is much more familiar with transforms because he or she uses them very extensively, I dare say that all engineering disciplines today cannot do without transforms. I think most of you will agree with me. In fact, you might use transforms either overtly or covertly. That means you might know that you're using a transform and use it consciously, or you might not quite recognize that you're using a transform and use it covertly. Either way, the transform is ubiquitous in engineering and also in science, and as I said, nowadays also in the social sciences. Having said that, let's now give a few introductory points before we start the active learning process. So, you see, what are we going to talk about in this session? We are going to talk about transforms. We'll of course first put forth what transforms are, what you generally mean by a transform. And we are going to see how you might want to introduce these and explain a transform to an audience. And remember, a transform is not one entity, it is several entities. In fact, many of the transforms are themselves several entities, right? And therefore, the transform is a collective word used more for a philosophy than for a particular operation or a particular technique. It's a whole philosophy in itself. Now let's spend a couple of minutes in understanding why we need transforms. Now let's begin the active process right from here. How many of you have in one way or the other used transforms in your engineering? You raise your hands. There must be many more. I'm sure there must be many more. Can you raise your hands? How many of you, for example, now when I ask you more specific questions, I think it will be clearer. How many of you have used the Laplace transform? That's now you can see, as I told you, overtly and covertly. So when I first said, how many of you have used transform, there were just about 3 or 4 hands that came up initially. And now when I say, let's see that again. How many of you have used the Laplace transform to solve differential equations? I can see, with the exception of a few, most people raise their hands. So it's very clear, that's what I meant. Now you understand what I meant when I said we use transforms overtly or covertly. When I said overtly, I could see that probably a few electrical engineers, maybe a few mechanical engineers raised their hands when I said transform. And when I said, the Laplace transform, then suddenly something clicks and almost all the engineers sitting here or scientists sitting here had something to do with the Laplace transform. So you recognize that transforms are needed. In fact, in some sense, the first question is redundant now, because all of you recognize that transforms are required, but still we need to discuss why transforms are needed. Now, again, I would give you, I would of course put forth before you a view that I have, but I would like you to put forth a view as well before we discuss this together. So let's follow the practice that we learned yesterday about think, pair. Take a minute, and now this time we'll be strict about time. Take a minute and on your notebook write down one reason. Don't write too many reasons. Only write one reason why you think a transform is required. And which transform, I think you should be more specific. Let's say you write down one transform which you're familiar with and why it is needed. And write it briefly, right? It's a think phase. So take only a minute for this. I repeat, take a minute to write down one transform with which you're familiar. Could be the Laplace transform, and why you think it is needed. Now, this is not a discussion phase. Do it individually. So let's be strict about time here. All of us done? Yes? Are we all done? Yes? All right. Now, take again just 1 minute and discuss with your partner, right, what you've written, and see if you have something new to learn from your partner. Take just a minute again. Or your group members, just take a minute. Again, we'll be careful about time. All right, I think the 1 minute is done. Now we would like to invite a few responses from groups. So now we'll all pay attention. We won't discuss among ourselves. And we'll pay. Now, which group would like to volunteer to give an answer? Yes, please. Yeah, okay, we have 2 of them. We'll give him a chance first. Yeah, you can.
My answer was for converting a complex differential equation into a form which is easier to solve.
Very good. That's nice. So, no, and did you answer which transform you're talking about? The Laplace transform. All right. Yes, very nice. Yes. Yes.
The Laplace transform. It is easy to calculation from time to time.
Okay. All right. Should we take the next group? I think we'll give it to the next group now. Okay. Okay. All right. Let me hear a few more responses then. Yeah. Any other response? Yes. There's one here. There's one here. I also request you to introduce yourself. It's nice for all of us to know one another. Yeah. Okay. Have you people discussed why they are useful? You're all right. Fine. All right. Any other responses? Yes, there's a response there. Okay. All right. Yeah. Yes, there's a response there. Okay. Hold the mic to yeah.
Find the solution and have it back the original domain by using reverse.
Okay, very good. Any other responses? All right. So this is the same group, right? So I think we have a response. Yeah. Any group wants to respond? Any other group? Yes. All right. So we've had several responses. I'm very glad to see that all of you are really picking up on the active learning part now. And let's try and summarize a few of the responses, a few of the points that emerged from the responses. See, many of you directly or indirectly talked about making the process of solution easier. So Laplace transform, for example, many of you, you said it in different language, but one indication was that somehow it seems to ease your process of dealing with a differential equation. You also give a different, the other point that seemed to come out was that you get different interpretations. So somebody talked about, now of course some people, I can see that this is an electrical engineers group, so they said time and frequency, but maybe that was not understood by everybody. But you know, the idea was that you could interpret differently, you could see things in a different light and therefore get a different interpretation of what the data was trying to convey to you. That is a point that emerged, which the electrical engineer calls time, frequency, or whatever other term he uses. So the other point that somebody brought out interestingly was that you go back and forth with a transform. So you don't just go into a transform domain and sit there, right? So there's something that you need to go to a transform domain and come back from a transform domain. So these are all the things that emerged from this. Now now naturally, in fact, in some sense, though I had not asked you the second question, that second question was implicit in some of your answers. Though many of you talked about the Laplace transform because the Laplace transform is known to most engineers and used by many engineers and scientists. Some of you also alluded to other transforms, the Fourier transform, for example. Somebody talked about a more general class of integral transforms and so on, right? So now let's see what my view is. You see, it is sometimes difficult to analyze a function in the original domain of representation. So for example, take a differential equation. When you write a differential equation, what are you saying? You're talking about rates of changes. And not only just rates of changes, rates of changes, rates of rates of changes. Rates of change of rates of change. And you're doing this, and while it's very easy to write d dt or write d dt squared or d squared d dt squared and so on, it's, interpreting this with data is not easy. So, and then a linear combination of these, even if you consider only linear constant coefficient difference equations, then in a linear constant coefficient difference equation, to say that some linear combination of derivatives is equal to some other linear combination of derivatives and then find out the function is very difficult to visualize, right? What are we doing in the Laplace transform, for example? We are saying, well, recognize the form of the equation, take advantage of some knowledge that you have about the nature of the solution, and thereby come to a simplification of what you do to arrive at the solution. So, in a sense, it is very difficult to analyze the differential equation in the origin. If you analyze it in the original variable where there is a derivative, it's difficult to deal with the equation, right? And it's difficult to come to a solution of the equation. So you try and go to a domain where the solution presents itself to you, right? And that's what the Laplace transform does. Now, of course, some of you may argue, for example, that in the solution of linear constant coefficient difference equations, that means differential equations, where the derivatives are combined by constant factors, as is the case with most of the problems of the Laplace transform, you know that the nature of the solution is of a particular kind, and you can always use the substitution of the function and then find out. But that's exactly what the Laplace transform does in a certain sense when you think about it. I'm trying to put before you a different way of thinking about the Laplace transform, because the Laplace transform is something that all of you, many of you at least, are familiar with, and I'm trying to put before you a different way of thinking about the Laplace transform just now, right? And this is to help you answer some of the other questions I'll raise in future. Now, the second point is that a transform acts as a tool to map this function to a different domain. In fact, many of you use the word domain when you answered. You said, well, you view the function in the original domain or the natural domain, and then you say, well, the original domain doesn't tell, it's too confusing to understand, so I view it in a different domain where things become clear, right? Where mathematical analysis and visualization is facilitated. Very good. Now, we'll keep these points in mind, but then we'll go further from here, and we are going to now again play certain games where we learn different transforms. Yes. Now we are going to do some active learning exercises. Let's begin with the first problem statement. And here, all of you need to participate in this. I'm going to put two problem statements before you. My purpose here is for you to identify what is common between the two problem statements, also to see what you would need to do. You see, nothing comes for free. if you wish to learn a transform, you must first identify what it is that you wish to achieve by using that transform, and then learn the transform and use it effectively. So we are first going to understand the real, you see, when is mathematics and engineering best learned? It is learned best when we understand the real life problem from which the need for using maths arises. We understand what features of the process, the real life, the real world issue demands use of mathematical techniques, and then we choose the mathematical techniques in an elegant way to deal with the situation that we have in front of us. Is that right? So with this background, I'm putting before you two different problem statements. The first problem statement is that you have, many of us, of course, I think almost all of us would have heard about the electrocardiogram, ECG. Many of you might know it as the ECG, right? How many of you have heard the term ECG? Can you raise your hands? Yes. I hope none of you have had to find out your ECG, of course, except for, a regular medical checkup. So, the ECG, as you know, is essentially a test for how your heart functions. The cardio, the word cardio, of course, refers to heart. And in the electrocardiogram, we essentially recognize that the heart generates electrical signals that we can tap at the surface. And from there, we can then identify how the heart functions. So abnormalities in the ECG would indicate abnormalities in the heart. Is that right? Many of you would know this. So obviously, when you are trying to record an ECG signal, you know that you use what are called ECG electrodes. Some of you may have seen how many of you have seen how an ECG is acquired? Can you raise your hands? Some of you have seen how an ECG is acquired. So what an ECG and when an ECG is acquired, you essentially place different electrodes at different points in the body. In fact, some of you might be aware that not one but multiple points of recording are used. So nowadays, with sophisticated ECG equipment, they don't just use one point of recording, they use multiple points, right? And it is inevitable that when you record a signal which has emerged in the heart but which is now seen on the surface of the body, there are going to be many other corrupting noises, corrupting signals. Some of the signals could be from the body, some of the signals could be outside the body. For example, they could be the electrical supply itself which creates an unwanted signal there, 50 hertz or 60 hertz signal, depending on which country you're working in, right? And there are many other sources. There can be ambient noise. So the ECG by itself is difficult to capture in pure form, right? So here you have the first, situation where there are typical noise sources. See, in fact, the body itself is respiring, so the body is breathing. So the body movements cause some amount of, ECG corruption. And those are very slow movements, of course. The body moves very slowly in respiration. So therefore, that kind of if you talk in terms of frequency, we're talking about less than 1 hertz of frequency there. And then power line interference, which is a much higher frequency, about 50 to 60 hertz. Right? So this is these are typical noise sources. In addition to them, there are so many other ambient noise sources and so on. So now this is the first problem statement. You want to remove noise from ECG. Now there's another problem, second. Now you see, this problem looks very different. But now I want you to think about it. See, here you have what is called an amplitude modulated wave. Now, I know that the electrical engineers might be familiar with this, but let's also make the other engineers or other scientists familiar with what we are doing here. So, you see, how many of you, I don't know, nowadays people listen more to FM, frequency modulated radio, but how many of you at all have listened to AM radio? You raise your hands? And nowadays nobody listens to radio at all, but how many of you have heard AM radio? Can you raise your hands? Yeah, a few of you heard AM radio. AM radio was, used in the more I think in the past. Nowadays a few stations would have AM radio. Now AM is a way of sending a message on a very high frequency wave. So for example, when you're transmitting voice over long distances, you're not going to transmit the voice as it is. Now, for example, in the traditional telephone system, what was done is to transmit what is called a baseband voice. That means the voice was sent as it was on the wire. Now that's almost never done. On the mobile, that is not done at all. So you're essentially taking the voice using what is called a carrier. And the carrier is another signal which can move much more easily in the intervening medium. Typically, it's a high frequency signal. So the voice is not a high frequency signal. How high can the frequency of our voice be? Probably not more than 400 hertz, 400 cycles per second. That is the highest kind of variation that our voice can give. But we are talking about frequencies that can easily go over thousands of kilometers without much attenuation or without much suppression by the medium. And that means you're talking about frequencies which are many tens of megahertz, sometimes even gigahertz. Right? Now, how do you transmit such a voice on a carrier signal which is so much higher in frequency? It is done by a process called modulation. So what you do is, you can visualize. Now, what is a carrier is essentially, so one way to think of a carrier is a sine wave. A sine wave could be a carrier. Now, sine wave, you know, has an amplitude, right? So that, I think all of us are familiar with sine waves. So a sine wave has an amplitude, and you could change the amplitude of the sine wave in accordance with your message. That's called amplitude modulation. So that's what the equation here says. Essentially, you've multiplied the sinusoid by the message, and you want to retrieve this message at the receiving end. That means you want to remove the carrier and retrieve the message at the receiving end. Right? This is another problem. Now, here I put before you two different real life problems. But I want you to spend a couple of minutes. Again, here we'll do the think, pair, share process. In the first think state, all of you must act individually, look at the two problems, and on your notebook, put down 1 or 2 points that you see are similar things in the two problems that you're dealing with. And secondly, what is it, if I wish to use a transform domain to deal with both these problems at the same time, what feature should that transform domain have? So this I would like you to put down individually first, and we'll take about 2 minutes to do that. Right, so 2 minutes, here this should be an individual exercise. So look at you understand the two problems that I put before you. You need to think and put down, I'm repeating. Firstly, what are the common things that you see in the two situations? There can be many other situations. If you can think of some other situations, welcome. Right? There might be other situations where these common things also apply. And then, having identified the common things, what do you think would be, what strategy should we follow in dealing with both the problems? Now, I know the electrical engineers have some advantage, but let's grant it to them, doesn't matter. I'm sure all the other engineers will also see something similar. So take 2 minutes on this. So this is an individual step, right? Don't discuss with your partners now. Put it down individually. I guess, you know, the gentleman there, we talk about individual. See, the think, pair, share, it's also a pedagogical process. So we must follow the pedagogical process sincerely. That means we don't talk to one another when we are doing the think step. So it must be an individual exercise. It doesn't matter if you're wrong, or that's not the point. The effort, the exercise is important. Put down your individual thoughts. And take 2 minutes for it. So I hope you understand. I'm saying put down what you see is common in the two situations and how you think you should deal with both the situations with a transform. Don't look at your neighbor's responses, even if you're tempted to. I see some of you are doing that. The temptation to do these things that violates the pedagogical process. It doesn't matter, you're not going to get a prize for the best answer or something. In fact, wrong answers are very helpful. In a class, in an active learning process, I mean, quote unquote, of course, certain things may not be wrong or right, but sometimes wrong answers are also very helpful. Yeah, just 2 minutes. Yeah, you want to ask a question about the process? Or you want to answer, respond? All right, yeah, we'll give you time for that. You want to respond or you want to ask a question? Oh, we'll just wait for... All right, I think many of you seem to be quite content with what you've written. Now we'll give you just 2 minutes again to discuss it with your group and then improve your responses or come out with a group response if possible. Only 2 minutes, please. Why don't you do that? Yeah, so the question, somebody asked me whether you want to write down what you arrive at as certain common thoughts. You're welcome to do that. Yes, it's a good idea. I would recommend that all the interns also, all our IIT students can also sit together. You can also sit together and discuss if you like. You can also sit there. Yeah, there are some students sitting there, so you can sit there and get to know them. Yeah, we're done with 2 minutes. So now let's all pay attention to the front. And now again, I'm very happy to see that some people were keen to respond even before we began, but now we'll invite a few. Now can I invite responses? So who would like to respond now and share? Yeah, all right, this time give you a chance. Yeah, please. Yeah, yes. Please introduce yourselves and then respond. Yes.
Myself, Manoj Kuleswar, I'm from GCSP. The common thing from their statement is that they are mixed signals.
Okay, very good. That's a good point. Yes, they are mixed signals. Yes. Can you explain what you mean by mixed signals?
Like this, in this problem, the UT contains carrier signal as well as message signal.
There are two different kinds of signals that have come together. Yeah, all right. Yes.
In solution, we have to separate out this.
Very good. Separation is needed. Yes.
Transform it into time domain to frequency domain.
There you have jumped a step because you know about this, but the others don't. So when you look at the situation, I agree that you need to separate, but when you want to separate, what common sense should you follow? Yes. Now, okay, very good. Thank you. We'll have a response from yes. Okay, that makes sense. Yeah, the word filter is something that most of us understand. Yes.
So there are two noise sources that you have shown here. One is respiratory body movement, which is 9.9 frequency. Another is power line interference, which is 360 hertz.
Okay.
So we can have a Wavelet transform or a particular bandpass filter. It can only carry it can only retrieve the.
Yeah, I agree with you. Filtering is required. So the word filter is something that most of us would.
Studying filtering, we need to see the signal in the frequency.
All right. I need to, so when I see it, so all right, yeah, let me hear a few more response. Yeah, who else would like to respond? Yes, there's a gentleman here. Yeah.
I'm not an electrical engineer.
Yes.
But I'm getting from this statement is that we have to demodulate our heart signal.
Yes.
So that the clearer picture of our heart rate will be seen.
Okay. So let me sort of modify that. In the ECG signal, we don't really use the term demodulation because you have not modulated in the first place. You have only corrupted. You have not corrupted. The process of recording corrupts. So you want to decorrupt it, not demodulate. The second case, yes, we want to demodulate it. A slight difference, but yes, yeah. All right. Yeah, there's a response from there. Yes, the back. Yes.
In the first case, the mixing is unintentional and
yes.
That is actually a negative thing.
Very good.
In the next case, that is the air modeling. It is actually intentionally done.
Yes. Very nice. Yes. Good. That's a good point.
Yes, this transform that is required, the physical signals are in side domain and we have to change it into frequency domain and then filtering can be done.
Okay, very nice. All right. Yeah. Here, yes, there's a response here.
I'm from computer science branch.
Yes.
So from both problems, with the first problem I'm very much clear. Basically, we are denoising means we are trying to remove the noise from the.
Yes.
So in computer science, what we do, we divide the image in the image processing. We divide the image into the matrices.
Okay.
In a matrix of a particular followed by a host, then we divide it into the branches of that, and then we apply our transform. So being a computer science, we can directly call that transform by using a predefined function that remove the noise.
But then the predefined function also needs to know which transform you want to use. So
As it is that a Wavelet, Wavelet type transform is used, and in the signaling part, we use filters. I did a workshop there, like upband filter and downband filters were called there. So in these types of the filters, if we want to remove a particular carrier frequency out of that, so we apply the filters in the sequences, we remove the branches out of the signal, and we get the original.
okay. Yeah, any other responses? Okay, there's a response here.
I just want to add that we can use frequency these transforms, frequency-based transforms, because the two signals are very different in frequencies. If the two signals would have been a similar frequency, then that would be a mistake. Since the amplitude modulated wave in message signal and carry signal have very different frequencies, that's why we can change it to frequency domain, and then we can separate it to signals. So,
okay, good. Any other?
Sir, in the first case, all the signal will be adding the signal, just like the random process, so we can't predict what frequency component will be adding the signal. But in the second case, we add a load frequency by VSC. So we can easily remove the signal, but in the first case, it is very difficult to remove all the frequency components because primary frequency from 0 frequency to frequency.
Okay, we'll take one response here. There's one response there. We'll take that response.
Here the scenario was that scenario in which two frequencies were added, while in scenario 2 these two frequencies are multiplied. So I think that scenario 1 I can apply a frequency transform and then a filter can filter out the frequency. While in scenario 2 a logarithmic needs to be applied to the initial state, and then a frequency transform can solve the problem.
Okay, I think there's one more there. All right. We want to this time we want to maximize the participation. Yes.
Actually, the first problem, Western knowledge, the second problem, switch off and on.
Okay, good. Thank you. Good. I think we have a good collection of responses now. Let me try and summarize some of the thoughts that emerged. You see, of course, I can see that there were people who are familiar, to some extent familiar with the subject, some people were not familiar with the subject, but the good thing is that everybody tried to respond. There were many people even who were not familiar with this subject who still are, and that's the whole effort here. We should also try to respond. Now, one thing that most of you recognized is that in both cases, you need to think in terms of sine waves. You see, in the first case it is obvious, the second case it is maybe not that obvious, but after you look at the problem carefully, you see that there is a need to think in terms of sine waves. So, in the first problem, of course, you know that the sine waves have been explicitly brought before you. The power line signal is very close to a sine wave, or should be close to a sine wave, and that's 50-60 hertz. And therefore, the interference coming from the power line can be thought of as a sinusoid or as a sine wave. And in some sense, even the body movements which are unwanted, the breathing movement or any other body movements, the breathing movement, for example, is a periodic movement. So you can think of it as many sine waves coming together, and there is a certain minimum frequency of the sine wave that you're dealing with. In the second problem, as somebody correctly said, instead of adding two sine waves, you've multiplied a sine wave. I mean, well, it's not if you take the message to be just a pure tone, you see, in the communication, people use the word tone. Tone means essentially a very pure sine wave. And the word tone also, there is a reason why people use the word tone. You know, the word, for example, a very good singer, a very good musician, when he renders a note, and if you recorded the note, it would look very much like a sine wave. It would be as, you know, that's why, you know, tone is a word that you would hear in music, right? So a person renders a tone. And if the tone is rendered well, if it is played, if it is sung well, it is close to a sine wave. And therefore, if one tone is being sent, for example, as a message, then you're not multiplying, you're not adding the tone to the carrier, but you're multiplying the tone by the carrier. So that is a difference which people saw. But then even then, you need to think of this in the language of sine waves to deal with it. So one of the common things that happen in both cases is that you need to shift your thinking from a signal which you have recorded in time to a signal which is a collection of sine waves. That's the first perspective that you need to change. The second perspective, as somebody said, is to filter. The word filter is something that all of us understand, whether it is an electrical engineer or a mechanical engineer or a civil engineer or a metallurgical engineer. I'm sure how many of you have heard the word filter, not electrical filter, but the word filter is something that all of us have heard, isn't it, at some stage or the other. You know, you filter out something, you filter out some unwanted part. You know, if you have some substances mixed together, you filter one out. And what do you do when you filter? In a filtering process, there must be first a way to distinguish the part that you want and the part that you don't want. So in a filtering process, you need to have a way to separate. So the word separation also came in some of the responses that came up. So that means the transform that you want to use here should first deal with sine waves directly. That means it must think in the language of sine waves rather than the language of what happens in time. Secondly, it should be possible to separate the sine waves. And thirdly, it should be possible, now this is a more subtle point, it should be possible to identify which sine waves you wish to retain and which sine waves you wish to remove. Right? So now let's see the answer. Let's take the next slide. So here the Fourier transform, by the way, the word Fourier is the name of a famous scientist. You know, I'm sure many of you have heard the term, must have heard that Fourier. You see, Fourier was, well, you can call him a scientist or a mathematician more than 3 centuries ago. When he recognized that if you have a periodic signal, you could think of it as a combination of sinusoids, a combination of sine waves. I believe that almost all of us, whether it is in the engineering discipline or in the science discipline, must have heard about the Fourier series, right? Maybe many of us have not heard about the Fourier transform, but many of us have heard about how many of you have heard about the Fourier series? Can you raise your hands? Yes, as you see, most of you are raising your hands, right? So the Fourier series, now the Fourier series is essentially a statement that I could think of periodic functions, at least a large class of periodic functions, leave out a few pathological cases, which are anyway not going to occur in practice, in terms of a combination of sinusoids, a combination of sine waves, all of which are multiples of a fundamental sine wave. The fundamental, of course, is the periodic function itself, the period of the frequency of the periodic function itself. Now, why should one want to do that? There are different reasons. One reason is that sine waves have some very powerful properties when you pass them through systems. So if you can think of a periodic function as a combination of sinusoids, then you can also deal with that periodic function very conveniently when it goes through a system, when it is acted upon by a system. You can understand what the system does to that periodic function more easily. Secondly, now a particular case of that is, if I wish to think of how to decorrupt a signal, as was the case for the ECG signal, or I wish to demodulate a signal, as was the case for the second problem, where AM modulation, demodulation was required, then it is easier for me to do it if I can first recognize which sine waves are there. And that's what the Fourier transform does. Now, here a pictorial representation has been given to you. Don't worry if you don't understand everything that is presented there. But some of you might be able to understand, but don't worry if you don't. I'll try and put before you the ideas in simple language. So, you notice the word filter occurs, right? So, you see, what does a filter do? Now, in a filter, the first thing that a filter must be able to do is to identify what you want and what you don't want. So the Fourier transform helps you do that. Now, having done that, you can identify, for example, in the ECG signal, you identify that the higher frequencies are what you don't want, right? And therefore, you put a low-pass filter. Low-pass filter means a filter or some device that allows the lower frequency sine waves to go through, and the higher frequency sine waves are impeded or stopped. So that's a simple way. Actually speaking, this is not quite correct, isn't it? Because you also want to remove the very low frequency, the 0.5, well, less than 1 Hertz frequency, which are bodily movements. So in a sense, this is not just a low-pass filtering operation, but anyway, it's a Fourier domain operation. Don't worry about the second part. But I know that some of you who are in the electrical engineering domain will recognize that what the second line says here is that once you take a Fourier transform, then the operation of what a filter does is easier to interpret in the Fourier transform domain than it is in the original domain. That's what the second line says. Is that right? So let's not bother too much about it. Let's take the second problem. Good. Now I'm twisting the problem. In fact, I'm going to a problem which, may I know your name please? Jitendra, which Jitendra brought before us. He said that as a computer scientist, I have sometimes dealt with images which have noisy, which are noisy. And I therefore put the next problem before. I want to denoise an image. What is meant by denoising? An image is often corrupted by noise during acquisition or transmission. And the important image features get buried with noise and affect the performance of. So now you see, very often you want to do something with the image. You want to identify something in the image. You want to sharpen something in the image. You want to, focus, or you want to zoom in or something in the image, or you want to change the characteristics of the image, whatever you want to do. In all these things, you want to segment the image, you want to classify the image, whatever you want to do. So in all this, you must first remove noise. So image denoising is a requirement. Now, what would you mean by denoising the image? You would want to retain the important signal features, but you don't want the noise to be there, right? You see, now we talked about the Fourier transform, right? We said in the Fourier transform, you essentially try to think of the signal as a combination of sine waves, and then you separated out the sine waves that you wanted and those that you did not want. But suppose it's not so easy to do it, which means this noise that you're dealing with is not easy to think of in terms of sine waves. So with the same sine wave, some part of it is signal, some part of it is noise. That means the Fourier transform is not a good idea here. So now, without going to the answer immediately, so let me put the problem differently before you. It means that in some parts of the image, it might be true that the higher frequencies are actually the problem. In some part of the image, it might be true that the lower frequencies are a problem, right? There's unwanted variation which is reflected more in the lower sine wave frequency, some part of the image. In some part of the image, actually it's a high frequency, it's the low frequency information that I want and the high frequency that I don't want. In some parts, it's the high frequency information that I want and the low frequency I don't want. So now, if you're given such a situation, then how would you deal with what if I want to design a transform for such a situation where I can separate the signal and noise? What characteristics should this transform have? Right? That is the question I'm posing before you. Again, let's take maybe 1 or not more than 2 minutes to put down individually what characteristics should my transform have given this situation, which is a slightly different from the previous one. And then we'll do so let's take only 1 or 2 minutes to write down individually what you think. Let's not go to the pair stage immediately. Let's first do an individual exercise. Let's do an individual exercise first. See, we have to be very sincere about the think, pair, share process. In the think phase, we must do it individually. Otherwise, the purpose of the think, pair, share is not fulfilled. If we start talking during the think phase, then it defeats the purpose of think, pair, share. So are we done with the think phase? Then we'll take only 1 or 2 minutes for the pair phase. That means you discuss with your group partners, what responses you have and come out with some common points that you've, take a minute or two for it. So here you must discuss very vigorously. All right, I think we'll have a share process now. So I think he's ready with a response. Yes. Do introduce yourself once again and give a response. What's the name? Brij Mohan. I'm so sorry. That, all right.
I think the answer I'm getting from this problem is we don't want higher frequency as well as we don't want the lower frequency. So
Okay.
There should be a range. Suppose we want 100 frequency. We can use RSB business working or something like that to filter out people with
Okay, all right, okay. Yeah, some more, yeah, there's a response here.
in this situation, we get response different for different frequencies, like at lower and higher frequency, and large high resolution and medium frequency that should be average.
Okay. Yeah, okay, yeah.
I think here I want to check the intensity variation between pixels. If there is a sudden variation, I want to know. First of all, I form a function for the matrix and then check how the intensity variation between d I by dt and then go for any lambda in the
Okay. Yeah, there's a.
So we can revise the window size. We can change the window size according to the intensity level. Then we can keep small size with the change in the region of the bar.
Okay, that's interesting. See, in fact, now listen to this response. What he said is, he used the word window. He said, I could look at different segments of the image and deal with them in a different way, and I could look at the characteristics of the segment and then use. So, in some sense, he's saying go local and also look at the local features. That's, yeah, yes, and yes, there's a response there. Okay, very good. Okay, so now he's brought in the idea of adaptivity. So you need to adapt something as you go along the image. That's okay, yes.
I think in this scenario, we want to add a filter which is non-linear. So I think that we can use a filter and additive information that we should have a specific characteristic. And by that we can introduce the non-linear.
Okay. Okay. I would like to hear from the non-electrical engineers also, yes. If any of the, whatever. It doesn't matter if you have, yes. Any other responses that you would like to give? Yes, there's a response here.
So here we can use, rather than operating a complete signal, we can use a strides. So we can use a memorization factor. So if any control signals are coming, so we can test that signals from the previous trained signals.
Okay, that's interesting. Okay, that's interesting. So here, that's an interesting idea. So you said, see here, she's suggesting that you essentially have a mechanism by which you fade out the part of the signal that you don't want and focus on the part of the signal that you want, and then try and identify. Yes, all right, yes, okay, yes, there's a response there.
So can you discretize the region that we use cross correlation from the addition cells in the particular cell design, and then through there identify the mechanism of it.
Okay, all right, okay. Yeah, any other responses? All right. Now, you see, here in this problem, as I said, we are dealing with a situation slightly different from the first two situations where you don't have a clear separation in the language of sine waves. But what you might have, so some interesting ideas that came up from the discussion as you saw is first, some people said, well, behave adaptively. So as you go along the image, adapt your strategy to where you are in the image. That is one idea. The second idea that came up was that you can block the image. You can divide the image into segments, and then you could deal with different segments differently. Now, both of these are very good ideas, and the issue that could crop up in each of these ideas is, in the adaptive idea, the issue that would crop up is what should be your mechanism of adaptation. In the blocks, the issue should be what should be your block size. You know, how large should the block be or how small should the block be, isn't it? So all these issues are addressed by something called the wavelet transform. So in fact, many of you might have, the electrical engineers might have heard, in fact now in many other domains also people have been, now which are the non-electrical engineers here who've also heard the term wavelet transform? Can you raise your hands? Yeah, there are a few non-electrical, can you raise your hands clearly? Yeah, you can see that there are some non-electrical engineers also here who have used the term, who have heard about the term wavelet transform. Now wavelet, let me explain to you. Wave is a sine, so sine wave is a wave which lasts for a very long time, right? A sine wave in principle lasts infinitely. A wavelet is a small wave. So the idea in the wavelet transform is that you have a localized wave. So you think of the signal in the language of localized waves. So in some parts of the signal, you might want to think of the higher frequency waves. In some part of the signal, you want to think about the lower frequency waves. So all this is done by something called the wavelet transform. Again, I'm not going into all the details. I've just put before this is the technique by which you calculate the wavelet transform. What I'll do is I'll flash an image with, yeah, you can just go. Now, go to the next one. Now here you have the original image here. This is by the way, for the people dealing with images, this is called a benchmark image. This is the so-called Lena image. And of course, one of the reasons why this image is used very frequently in image analysis or image processing is that it has almost all the kinds of features that you might want in an image processing situation. That means it has very smooth parts. And it has also very, very textured parts. And it also has some parts which are edgy. There are edges, right? And so it has all the challenges that an image poses. The smooth part, the smooth background, or the edges, or the textured part, right? Or the part, and there are different kinds of edges. You see that there are diagonal edges here, there are vertical edges here, there are also horizontal edges here. You can see there are some horizontal edges here. So there are all kinds of edges, right? So because of this is an example of what is called a benchmark image. So here, this original image has been corrupted with noise. So it's a noisy image, and then we could denoise it with the wavelet transform. Now go back to the previous one. Now this is what the two-dimensional wavelet transform would look like. Now I don't know if you can see it at the back. Actually, can you see that in this part of the wavelet transform, you see a predominance of the horizontal. Can you see it from a distance? Or is it not visible? It's not so visible. Okay. So anyway, here you see a predominance of the vertical. But here you see a predominance of the horizontal. Now this is very weak. There is a predominance of the diagonal here, but that's very weak in this particular decomposition. Here you might see, and you see, the same predominance of the vertical and predominance of the horizontal is seen at different resolutions. And what you see here is a coarse version of the original image. Now this is what a typical two-dimensional wavelet transform looks like, which means in different parts of the image you have identified features which are peculiar to that part. In some parts where there is horizontal information, you see horizontal information magnified in the horizontal part. In some parts where there's vertical information, you've identified vertical information, and again vertical information at different frequencies, different levels of variation, right? So this is what a wavelet transform does. It allows you to deal both with the original domain and the frequency domain at once. So earlier the Fourier transform took you entirely to think in terms of sine waves. The wavelet transform allows you to think both together. The original domain, time or space, and also sines. Right, so this is, of course, it's a whole subject by itself, so I can't tell you everything about the wavelet transform in these 5 minutes, but let's now go to the next problem. Now, this is, of course, something that all of you are very happy with. So of course, now you want to solve differential equations. You want to, in fact, some of you would tell me the answer right away, but let's still go through this process. So you want to solve differential equations. You know that differential equations are used in many fields of science and technology, and solving a complex or higher order differential equation is a difficult task. You need to have a technique to solve them with minimal effort. Yeah, next. Now I'm putting this time as a variant, we'll put an example of a mechanical system before you. Right, so here I have a very simple mechanical, all of you will understand this system. There's a simple mass which is acted upon effectively by three agents. There is a force which is represented by F. There is a damper. Now this damper is a way of showing resistance or frictional counteractive forces. So that doesn't mean that you actually have a damper there. That's one way of representing, that's one way to represent the frictional features that might be present in the system. And you might have a spring. There might be some spring action. Now, this is how, so you see the position of the mass is represented by x. So the derivative, of course, you know that when a mass is acted upon by a net force, then there's an acceleration in the mass. All of us know this, right? And the acceleration comes from the net force. So what is the net force? The net force is Ft, F is a function of t, minus some, so now you know there's a component which is caused by friction, which is proportional to the derivative of the position, the velocity, and there's a component which is caused by the spring action, which is proportional to the displacement. So that's what this first, the left hand side says, and the right hand side says that the acceleration, mass times the acceleration, would be equal to this net force. Is that right? Now you want to solve this differential equation, right? So how would you solve the differential equation? Now, of course, here I think all of us know this, so I'm not going through the exercise of think, pair, share, but let's see. So you have a differential equation, you take the Laplace transform, so now you get an algebraic equation. Now, so you know, many of you know this process, right? So you take the algebraic equation in terms of the Laplace transform, and then you solve the algebraic equation and you get the solution by inverting the Laplace transform. Now, I think many of you are aware of this process, so I'm not asking you to do a think, pair, share, but I'm asking you to do a think, pair, share for a different reason, right? The think, pair, share I want you to do is take a minute to write down why you think the Laplace transform works. Why do you think the Laplace transform goes from a differential situation, which is difficult to deal with, to an algebraic situation, right? So that is what I want you to take a minute to write down what you think your answer is. So first the individual step. Take a minute to write down individually and then we'll discuss it. Why does this Laplace transform work? What do you think is the mechanism by which it works? The question is, why do you think the Laplace transform works? Write down your individual thought first. Many of you know about the Laplace transform. Have you thought why it works? Why does it go from a differential situation to an algebraic situation? And thereby ease your problem solution. How does it manage to do that? So take a minute to think. And now we'll allow you 1 minute to discuss among yourself in the group. Okay, shall we have some responses? What you think? What could be the answer to this? It's not such an easy question, no? Actually, it's not very difficult also. Let me see, yeah, if there are any responses that I hear. Yes, there's a response there. So why do you think this worked? Yes.
When we solve the differential equation, then we have to solve the complementary function. So doing this is a very rigorous process. It
Fine.
takes a lot of time, but if we use the Laplace transform, then conversion from means it is very easy. Solving an algebraic equation by using partial fraction is very easy process. So it saves our time and it is a perfect solution.
No, I agree with you. So that if all of us appreciate. What I'm asking is, how did this Laplace transform manage to make your solution easier? What was the magic it did? Okay, any other responses? Yes, okay, there's a response here. Okay. Okay, yeah, that's actually very good. Yeah. That's very interesting. Actually, that brings up two very interesting ideas. One is that, so he talked about making an unbounded signal bounded, and the other thing he said was a function of the form e raised to the power sigma, or e raised to the power sigma t more. Okay, that is so. Yeah, let me hear some more responses. Yes, there's a response here. Good.
So probably it transforms differential or integral equations from polynomial equations.
Very good. Agreed. Yeah, you're right. That's that. It does that. How does it manage to do it? What is the secret? That is what I'm. Yes. Any other? Yeah, there's a.
Also, from multiple functions which we have as problems, we try to convert them into like logarithmic or exponential terms. It's easy to calculate it further or integrate.
Very good. That's a good point. So in fact, there's a hint which he gave that you're trying to think in terms of a different class of functions, the exponential functions, so the logarithm, not logarithm, the exponential functions. All right, that's yes. Yeah, any other responses? Yeah. So very good. So, it's very interesting that some of you, were on the right track in thinking about your answer. Let's go through the solution. So here, if you look at now all of you, or at least many of you might remember this expression for the Laplace transform, right? This is how you calculate the Laplace transform of a function. You multiply the function by e raised to the power of st minus st and integrate. Now, in a way, what are you trying to do when you do this? Now, I will illustrate to you how one of the responses is captured here. See, you are now thinking not even in terms just of sine waves, but in terms of sine waves, or rather rotating complex numbers which are multiplied by an exponential factor. You are trying to think in the language of such functions. Why are you doing that? What is the speciality of the function e raised to the power of st? Now take a minute to reflect upon this. Again, this time we'll do the reflection fast, half a minute. So you can think individually what is the speciality of the function e raised to the power of st, half a minute. So we take the think and pair sessions together. So in 1 minute, I want you to think in your group. What is so special about e raised to the power of st? And I'd like to hear some responses. So Laplace transform is based on e raised to the power of st in some sense. What is so special about e raised to the power of st? And there our minute is done. So now let me hear some responses. Yeah, any response? Ready? What is so special about e raised to the power of st? Yes, there's a response there, please. Okay. So what is special? Why are we so fond of it? Why have we used that in this transform? Yes, there's a response there. Yes, loudly. Well, in a way, yes, what you're saying, but then I would like to hear a more accurate or something. Okay, yes, there's a response there. Pass it to him. Yeah.
My name is Rajkumar and I am from Party. E raised to the power st is constant by integration.
Very, very. Can you say a little more about what you mean by that?
If we integrate or differentiate, it gives the same value.
It doesn't give the same. It gives the same form. Very good. Yes, that's a very good response. So here, if you look at e raised to the power of st. I remember there was this in my undergraduate days, so as the lighter vein. So, they had formulated a joke about this e raised to the power of st. He said that two people are going to have two functions are having an argument. So the one function says, तुमको मैं differentiate कर दूंगा, integrate कर दूंगा. Other function says, मुझे कोई फर्क नहीं पड़ेगा, कौन सा function है. Right? So which is that function? E raised to the power of st, isn't it? कोई फर्क नहीं पड़ता. कोई फर्क नहीं पड़ता मतलब the function retains its form. Right? And that's why the differential equation now becomes, now what is okay, it retains its form, but what is important is that for a linear constant coefficient differential equation, the nature of the solution also can be thought of as a combination of e raised to the power of st's and polynomials multiplied by e raised to the power of st's. And therefore, in some sense, you are making use of the knowledge of what kind of solution you expect to formulate a transform here. That is the secret. Is that right? That's why the Laplace transform works so well. Very good. Now let's go. Now, of course, by the way, yes. So, you see, the Laplace transform works for two reasons. One is that you are sort of making use of your knowledge of what kind of solution you expect. So when you have a linear constant coefficient differential equation, you know that the solution can be expressed as a combination of what are called poly-x terms. Polynomials in the original variable multiplied by exponentials in the original variable. So e raised to the power of st multiplied by a polynomial in t. So you know that that's the kind of solution that you expect. And you are therefore formulating a transform based on this knowledge. That's what the Laplace transform is doing. Right? The second thing is that e raised to the power of st remains as it is in form after differentiation or integration. Right? So, yeah. So this is an example. You can go through it. It's on the Moodle page. We need not run through it. But one important thing about the Laplace transform is that you can also use the Laplace domain to bring analogues between different kinds of engineering. So the same mechanical system that we had can also be thought of as equivalent to an electrical system, right? So you could think of a mass, well, there are different ways to do it. You could think of a mass like an inductor, friction like a resistor, spring like a capacitor. You can also think of it the other way. You could think of a spring like an inductor, mass like a capacitor, and friction like a resistor in both cases. And therefore, the Laplace transform also helps you bring commonality between different domains. So you could think of a mechanical and electrical system in the same language. Right? And you could solve and then arrive at conclusions about a mechanical system and electrical system at the same time. Yeah. So you could convert, so that is what this is essentially saying. You can run through this. Now this is an example of an electrical system which would mimic that mechanical system that we drew. Alright. Now let's take the fourth exercise. Here I will run through the solution myself because I want to take you to some other problems. Now suppose I want to compress an image. So so far I want to denoise an image, now I want to compress, I want to represent the image more efficiently. And you know why we want to compress an image. Now all of you use so many images on your mobile, so it's obvious that the mobile, if it has to store images, can't store it in the raw form, it has to store it in some form which is efficient. So you have to compress the image in some way. So nowadays, although people may not really be signal processing engineers, most people have heard the term JPG image bhej diya, isn't it? Or PNG image. So these things are well known, but people don't know what is behind it, right? So what is behind this? So this is the problem before you. What is behind this? Now this time we'll take only 1 minute. So 1 minute, try and think what is behind this image compression that you do when you use images on your mobile or on your computer. Take 1 minute to think individually. Yeah, think now. Take 1 minute to think individually. What does it do when you want to compress images? What are you really doing? And now take less than a minute to discuss in your group. And now let me hear responses. Any response? Yeah, there's a response here. You have a response? You have a response? Yeah, okay, let's give her the yes.
Sir, I'm Gadre from BCHP. Sir, in this level, we can convert high dimension features into low dimension.
Very good, yes. Very nice, very good. That's a good idea, yes. So yeah, there's a response there.
If I go to the image vertical coding, the pixel becomes larger than we can specify this number of bits. The pixel becomes so very less we can larger.
Very good. That's a very good idea. Yes, yes, yes. Yeah. Any other responses? Very good. Now let's look at the. Now there are two ideas here which came up. In fact, I was very happy to see two ideas. One of them which is not here yet. I'll still talk about that. So one idea, as Professor Chaudhary said, you want to see a domain in which you can represent high dimensional information by low dimensional. That means, you see, now think of it like this. Now think of this chalk as a vector, right? Think of the chalk as a vector. Now this is the paper that I have here can be thought of as the horizontal plane, and there is a vertical line. So this is the three-dimensional world, and this is a vector in 3 dimensions. Now, if I want to represent this vector efficiently, what is one strategy I can use? Instead of using this horizontal plane with its xy and then a vertical z, I can orient one of the axes along that vector. You see what I mean? So if one of my axis x, y, z is along that vector, then I need only one component to represent the vector. I don't need 3 components. So in a way, that's what image compression tries to do. It tries to find an orientation of the axis which best captures the image information. And one good way to do that is using something called the discrete cosine transform. Right? Now this was the idea which Professor Chaudhary gave. There's a very other interesting idea which I forget your name again. Amit, which Amit gave, Professor Amit gave. And that is, suppose you also look at the bit patterns, not only the representation of the data, look at the bit patterns. If your bit patterns show that there is a large sequence of zeros or ones, or there are certain patterns of zeros and ones which occur more frequently, use a more efficient way to represent the patterns. Right? So this is also used. This is called Huffman coding. This is called, so there are 2 kinds of techniques used in image compression. One is of course the transform technique, and the other is what is called the bit level coding technique. Yeah, very good. Yes. Yeah. So this is an example of a 2-dimensional DCT basis. So the functions that are used to, yeah. So this is of course the process. Yes. Now maybe we'll take this as the next example, and maybe we should conclude with this. I'll just then flash the other transforms before you, but this we'll do as a think, pair, share exercise. Now I have a very important problem of computer tomography here. So what do you do in computer tomography? In tomography, what you're doing is, you are essentially taking, so you want to image a certain part of the body, right? So what you do is, you send rays of electromagnetic rays through the body in different orientations, and you see how the body responds to these rays, right? So you pass the ray passes through different segments of the body, and how the ray behaves when it goes to the body is recorded for different dimensions, for different directions. That's called computer tomography, right? CT. Again, many of you may have heard the term CT scan. How many of you have heard the term CT scan? Many of you may have heard the term CT scan. CT is computer tomography. So what you do in computer tomography is, you essentially pass electromagnetic rays in different directions in the body at different regions, and you record how the ray is received, and based on that you come to a conclusion on what is inside the body, the inner parts of the body. So a CT scan can be used to diagnose and monitor a number of different health conditions. This is the real life problem you want to deal with. Yes. Now I'm giving you a hint. We want to design a transform to deal with this, right? So I'm giving you a hint. The hint is that you could use what is called the Beer-Lambert law, So even if we don't want to be very, very formal about this, what we're trying to say is, essentially when you send a ray through different parts of the body, it is the way the ray is absorbed and received that gives you information, collective information about the path of the ray. Right? So the entire path of the ray is captured by the collective attenuation faced by the ray as it goes through that segment of the body. So this is the idea used in computer tomography. So now doesn't matter, the name is not important, but now I want you to put down, now this is a slightly more difficult, not so simple. But now I want to design a transform which will deal with this CT scan. That means I'm getting a CT scan and I want to get information about the original 3D volume or 2D situation. Let us first make it simple by dealing with a 2D situation. So you have a two-dimensional pattern and you're essentially looking at it along different rays, right? And you want to infer the 2D pattern from what you get at the received rays, right? Now, what should be the features of such a transform which can help us do this, right? So now, again, I want you to spend 2 minutes thinking about it individually. So please think about it individually. Put down the features of the transform that you should have to deal with this situation. So this time it's a think process. So first think on your own. Put down. Take 2 minutes and put down. Yeah, so think stage is done. Now we'll have the pair stage where you can discuss in your group. So for the pair stage will take about 2 minutes. Yes, so can we have some responses now? Yes, yes. What would a transform here need to do? Slightly, I know it's a slightly more difficult question. Any thoughts? Yes, all right, very good. So Amit has an answer, yes. Okay.
After that, what intensity we give, from the intensity we can get many to get one. So on this basis we can convert over.
Okay, so that's an interesting. So he says that you have a many-to-one mapping here, so you need to get out of that many-to-one situation. How do you do that? Okay, yes, all right, yes. Any other responses? Yes, there's a response here.
Here we have a collection of races. So
Yes.
we want to use that collective information to make an image of a body.
Yes, yes.
So here, but we don't know what are the directions of the wave
That. Well, let me correct you. You might know. So you might very well, control the directions in which you send. Okay.
We can use the eigenvalues and eigenvectors for collecting the information of the waves and connecting that points and try to make the image.
Okay, all right. Okay, that's an interesting thought. Okay. All right. Yeah. Any other responses? This was any other? No. All right. This was a slightly more difficult one. Yes. Now here we use something called a radon. Another radon again. The radon transform. Now the idea here. See, what do we need to do in this situation? See, what are we doing in this situation? You're integrating functions along different lines. So you're finding some sort, as somebody said, it's a many-to-one mapping. So you have several variables which have got mapped into one intensity. But you're doing this along many different directions. So even though it looks like a many-to-one mapping, actually it's many many-to-one mappings. You see what I mean? There are several many-to-one mappings. And from those several many-to-one mappings, you have to get back the many from there. Now how do you do it? Well, so this is the situation. You have essentially looked at several different rays which are giving you an intensity, and you've mapped those intensities as a function of position and angle, isn't it? Yeah. So you need to back project. So you have several different projections, and now you need a transform which can take you from the projections back to the original two-dimensional information. That's what the radon transform does. And the radon transform, therefore, needs to go to a different way of dealing with the image. The image, initially you deal with as an XY pattern. Now you have to deal with it in terms of radius and angle. So you think of the image as having information radially and angularly. And that would give you an insight into how you would. So you see, you can think of it like this, that along different radial patterns, you've got some information. You've got this as a function of the radius and the angle. Right? Now you want to reconstruct the image in terms of radius and angle. Right? No, go back there. So, though I'm not going into all the mathematical details of the radon transform, the central idea here is that you think of the image now not as an XY pattern, but as a radius R theta pattern. And then you formulate an inversion strategy based on this R theta pattern. That's what the radon transform does. Alright. Now to conclude, I will just flash one more transform before you. This time I won't do the think, pair, share. Yeah. So now this is a very common problem. You know that many of us use the Aadhaar card, and there the Aadhaar also captures the iris. And if I wish to recognize the iris pattern, then yes, go on. How would I recognize the iris pattern? I need to recognize certain particular shapes in the iris pattern. So what should my transform here do? The transform should focus on those shapes. So that's what is called the Huff transform does. The Huff transform essentially helps you focus on different shapes that are present in the image, right? Alright, so you could have a Huff transform which focuses on lines, or you could have a Huff transform that focuses on circles, alright? And therefore you could use a Huff transform for iris localization, which essentially captures certain patterns that are typical to an iris, right? You could design your Huff transform to focus on certain shapes. Well, we are running out of time, so we will conclude the lecture here. Now, you're most welcome. We won't, we've been having discussion on the way. Maybe we'll take one question. There is one question we can take, and then we'll disperse and we'll reassemble at 11:30. Let's take, if you have any questions, we'll take one question, one or two questions. Yeah. Yes. What is the difference between CT scan and MRI? In the CT scan, you're essentially sending electromagnetic radiation in different directions, right? And you're looking at the collective absorption along different directions, and you're reconstructing the image from there. What is the difficulty with this? One, to some extent, it is harmful because you're sending X-rays into the body. So it does depend on the body being irradiated. In contrast, what the MRI does is, it simply puts the body in a magnetic field. And now, there are certain inherent magnetic behaviors the body molecules exhibit. So you change those behaviors momentarily, and those changes are recorded by the MRI. So here, the invasion on the body is less, right? Although the only invasion the body suffers in MRI is that it needs to be put in a strong magnetic field, right? And of course, therefore, you know that if you want to get an MRI scan done, all articles which have any magnetic character have to be kept away, right? Because they will interfere with the MRI. But it is less invasive on the body. Yes? Okay. We'll have to conclude this lecture here, and we'll reassemble at 11:30. Thank you so much.